All right. Um, okay, so good morning, everyone. Welcome to Lecture 3. I am still able to keep track of the number. Let's see how long that lasts. Okay, so we discussed a bunch of things yesterday. If there are any questions or concerns pertaining to that, feel free to ask them right now. Okay, if not, let's recap the minimum cost perfect matching problem. We want to continue talking about this today. Um, and we'll just get started with what the problem is once again. So we have a graph and we have a cost function which gives a cost to every edge of the graph, which is the cost is a real number, right? So these are constants, these are not variables. So we'll refer to the cost of edge ei as CEI. And what we want to do is we want to write down an integer linear program like we did yesterday for finding a minimum cost perfect matching in this graph. Right? And for the sake of our example, we are going to look at this graph. My motivation is to introduce the matrix vector notation for writing an ILP or an LP. Okay. And then we will talk about more deeper concepts regarding the minimum cost perfect matching problem. Okay. So for this graph, well, we are trying to minimize the total cost of our perfect matching, right? So that would be CEXE. XE is our indicator variable. It indicates whether the edge is in the perfect matching or it is not in the perfect matching, right? And this is over, right? So this is over all the edges of the graph. And subject to, which I said as I will abbreviate from now on to just S dot T dot, we have some constraints, right? And what are our constraints? Our constraints are that for each vertex, we want the sum of the variables corresponding to the edges incident at that vertex. We want that to be equal to 1. So I'm going to actually explicitly write down the constraints in this particular example. Okay. So let me put down all the vertices V0, V1, V2, and V3. Okay. We are going to have constraints for all of these vertices. So for V0, we have the edges E0, E2, and E4. XE0 plus XE2 plus XE4. We want this to be equal to 1. Okay. For V1, we have E0 and E1. So it's XE0 plus XE1 equal to 1. And for V2, we have E1, E2, and E3. So this guy, and this guy. And finally, for the vertex V3, it's just E3 and E4. Okay, so these are all of our constraints, one for each vertex. We also have, these constraints are often called the degree constraints in the context of the perfect matching problem, because it's saying that the degree of each vertex in a perfect matching, if you just look at the graph formed by those edges, the degree of each vertex should be equal to 1. Okay, so in the context of this problem, we will refer to them as degree constraints. On top of that, we want that each variable is non-negative. Okay, for each edge, we have this. These are called, of course, the non-negativity constraints. And this is going to be a fairly standard term when we are talking about linear programs and integer linear programs. Okay. And finally, because we are writing an integer linear program, we also have the integrality constraints. We want each variable to be an integer. Okay, and such constraints will only appear in integer linear programs. You can't have these constraints in linear programs, and these will be called integrality or integer constraints. Okay, are there any questions or concerns regarding Anything so far?
Sir, what if
Yeah, go ahead.
xi is given to be even a negative number? So here we are forcing it to be non-negative. If we put it as a
Yeah.
negative number, does it, does the solution space blow up again or something?
Um, so I
So if
guess, I
we,
mean, in this context, yeah, go ahead. Yeah.
yes, sir, just wanted to know what if xi, somewhere if that term is the non-negativity constraint is not there, what happens to the solution
Mhm.
space?
Well, that depends on the particular graph you are looking at. So I would suggest trying it out. Take some example and see if you can actually make it negative and get other interesting solutions. I mean, it's not interesting in the context of perfect matchings, right? Because we want to formulate exactly the minimum cost perfect matching problem here. But definitely, there is no such. I mean, in general, for linear programs, we don't need to have non-negativity constraints. So we will see examples where the variables xi's or some variables are allowed to be free variables. Free as in they can be negative, positive, whatever.
Okay,
Right?
understood.
Yeah. So in this particular problem, we just want to formulate the exact minimum cost perfect matching problem. So we are having this constraint, but we don't need to have all variables to be non-negative in general. Does that answer your question?
Yes, sir. That's what I wanted. I just wanted to know if xi in any case will be negative, or it's a hard and fast rule that
No, no, no. So in general, we are going to allow all possibilities. We just want the program to be a linear program or an integer linear program in this course.
Okay, okay,
So,
I got that.
yeah. So within the bounds of how we define things, we will allow depending on the problem we are looking at. Okay, good. Um, so related to that point, I also want to mention that in this problem, the costs on the edges are allowed to be negative as well. Okay, so we are not restricting the costs to be non-negative. We will allow negative costs because the theory works out even in that case. Okay, good. Any other questions or concerns? Okay, so the reason I wrote this down completely is because I want to write this down for this example in the matrix and vector notation. Okay, just for the sake of one example, and by that we will talk about the incidence matrix of a graph in case you don't recall what it means. Okay, so what I want to do, so let's start with the easy parts. So we want to rewrite this LP, ILP as follows. Okay, so the we are going to have a vector for the variables, which is going to be our column vector x e1. I think we have e0, e1, e2, e3, e4. So we will have this vector starting from e1 up to e4. Okay, and if you want to use matrix and vector notation, let's write down the objective function. So we also have a cost vector similarly, right? This is also from the cost for edge ei up to cost of edge E4. Okay. And what we are trying to minimize is C transpose X. Does everybody agree? Everybody familiar with vector multiplication? Okay. And now I want to write down the constraints also using vectors and matrices. Okay. So how would we do that? Any suggestions? How should I write down these constraints? I want to focus on the degree constraints and I want to write them down using vector and matrix notation. What should my matrix look like? And what, I mean, the vector is clear, right? So we are going to multiply by the vector x. And what should our matrix be?
Something with ones and zeros. Like,
Okay. So the rows are indexed by,
like the incidence matrix.
exactly, it's the incidence matrix. So we are going to index the rows by vertices as you see in these equations. And we are going to index the columns by the edges of the graph, right? Okay. And notice that for vertex V0, we are going to put ones in E0, E2, and E4 columns because those are exactly the edges that are incident at the vertex V0. Okay, V1 is going to have ones here, V2 is going to have ones in these three positions, and V3 is going to have ones in the last two positions, right? And the rest are all zeros. And this is exactly what is called the incidence matrix of a graph. Okay, so in case you don't recall, this is what it is. This is the incidence matrix of the graph. In this example, I'll just call it A. But if the graph is G, then we are going to write it as A of G in case we need to specify which graph we are referring to. Okay. And what do we want this to be equal to? Can someone tell me what the right hand side is?
All one.
All ones. So we want it to be the all ones column vector. Right? And I'm going to just underline it to indicate that I am referring to the all ones column vector of the appropriate dimension. Right? We won't write down the dimension because it's clear from the context. Okay. And how do we write down this constraint? Well, that's easier, right? We just want the vector x to be non-negative, which means that all the components, each component is non-negative. So we are just going to write this as x at least 0. I'm referring to the all zeros column vector. And I want the vector x to be integral. Sometimes I might just say integer, but what I mean is each component is an integer because a vector cannot be an integer, right? Okay, so let's write this down again. So what we have is minimize C transpose X subject to the matrix A times X equal to 1, X being at least 0, and X being an integral vector. Okay, and this is a compact way to write down the problem, the ILP for the minimum cost perfect matching problem, right? So I'll just call this ILP for min cost perfect matching. Okay. And the reason I wanted to talk about this, take some time, is I want everybody to be very familiar with this notation, right? If you are thrown off by vector and matrix notation, just expand out things and try to understand what it's trying to say. Okay. So we are going to be using this compact notation for most part of the course, rather than writing down every single constraint. Okay. So are there any questions or concerns regarding anything we've discussed so far? Okay. All right. So, let's see. So maybe I should say, maybe I'll just make a quick point here. A of G is the incidence matrix of the graph G, where rows correspond to vertices and columns correspond to edges. Okay, and ai comma j is equal to 1 if and only if um, vertex I, maybe I'll write in notation, edge ej is incident at vertex vi. Okay, cool. So we'll find this matrix to be quite useful for various problems we'll be studying during this course. Okay, so now I want to take a turn here into a slightly different direction. Okay. So I want to give you an example and I want to have a discussion which is going to be slightly geared towards complexity theory. So, how many of you are not familiar with the complexity classes NP and co-NP? Can you raise your hands or can you write in the chat box? And if you're not familiar, don't worry about it. This course is not a course on complexity theory, but I do want to give you a perspective related to that. So, the complexity classes new to it. Okay, Nitin, thank you. That I want to talk about, but we will keep the discussion as far as possible, not too tied to that. NP and co-NP. So most of you or many of you might have heard of NP. Not sure if you recall the formal definition, but we don't need the formal definition. I want to talk about it at the intuitive level. And co-NP might be a bit less familiar. So can anyone, if you don't know about these, can you please mention in the chat box or raise your hands? Okay, thanks, Ravi. Thanks, Kshitij. Okay, thank you. Good. All right. So it doesn't really matter. This is not a course in complexity theory, but so let's start with a slightly more intuitive discussion. Okay, and I want to give you an example. So let's consider the following graph. So here is a particular graph G. I want to label the vertices R, S, T, U, V, and W. Okay. I won't label the edges. We will just refer to them by their endpoints. Okay. And I'm going to put down costs on the edges. 3, 1, minus 1, 2, 3, minus 1, 1, 4, 7, and 9. Okay. All right. So let me point out a particular perfect matching here. Let's say I point out a red colored perfect matching. It's going to be this one. VW, RU, and ST. Okay. So the red colored perfect matching, we are going to call it N. And N is equal to these three edges that I have marked. Okay. So what is the cost of N? Nine minus one equal to 7, right? Okay. We will just call it C of N. And in general, for a subset of the edges, well, mostly we'll be interested in matchings. But if F is a subset of the edge set, C of F is going to be generally the summation of the cost of all edges that belong to the set F. And so this is our graph G, and we are given a cost function. Right? Okay. So I prepared this example, which is why I know that this is not a minimum cost perfect matching. But I want to ask you, how would you convince someone that this is not a minimum cost perfect matching?
Showing them another matching which has a lesser cost.
Exactly, exactly. So that's exactly the answer I'm looking for. So Right? This is easy. If you want to convince someone that n is not a minimum cost perfect matching, then you just show them a perfect matching whose cost is lesser than n. So maybe just display or show a perfect matching n such that the cost of m is strictly less than the cost of n. Right? This is easy. If I mean how you find m, that is the algorithmic question. We are not talking about algorithms here. But if n is not a minimum cost perfect matching, then it's precisely because there exists a perfect matching m whose cost is strictly less than the cost of n. Right? And if you were somehow able to magically find this, then you would be able to convince the other person that n is indeed not a minimum cost perfect matching. Okay? So now let me phrase this in the terms of complexity theory. Okay? And I just want you to have this viewpoint because a lot of things we are going to discuss in this course, if you view it from the lens of complexity theory, it all fits together really nicely. Okay? So, theoretical computer science is full of decision problems. It's one of the main objects of interest in computer science in general, right? So, I want to give you a specific decision problem. I'll call it DP, min cost perfect matching. Okay, and you are given a graph G and edge costs and you are given a perfect matching M, let's say, of G, and your task is to decide whether M is a minimum cost perfect matching or not. Okay. So if the given perfect matching is a minimum cost perfect matching, then you would say yes, otherwise you would say no, right? So there are two kinds of instances, yes instances and no instances, right? So in our example, we were given a perfect matching that is not a minimum cost perfect matching. Can someone actually find me a perfect matching whose cost is lesser than n in this small example? So can you quickly examine the perfect matchings and see if you are able to find one
Yeah.
which has lesser cost? Yeah, go ahead, Krishnan.
VU, RT,
VU, RT,
and WS. Yeah.
WS. Exactly. Thanks, Krishnan. Thanks, Ashish. Yeah. So let me indicate that perfect matching in green color. So it's VU, RT, and SW. Right? It doesn't have to be unique, but in this example, I actually know that it is a unique one. So that's going to be easier to discuss. Okay, so this is our perfect matching M. Okay, for this example, it's VU, RT, SW. And observe that the cost of M is exactly equal to 6. Okay. So if you were to show somebody this perfect matching, they would be convinced that the original one, N, the red colored, is not a minimum cost perfect matching. Okay. So that means that for a yes, decide whether M is a minimum cost perfect matching. So that means that for a no instance, when it is not a minimum cost perfect matching, there is an easy way to demonstrate that. This is going to be called a certificate. So you can, M is a certificate for convincing someone that N is not a perfect matching. Okay. So observe that in our example, M is a certificate to convince someone. So we are going to use the term certificate because it certifies that the given perfect matching N is not a perfect matching. Okay? And observe that such a certificate must exist. Whenever a perfect matching is not of minimum cost, it is precisely because there is a perfect matching whose cost is lesser than the one you are looking at, right? So because a certificate always exists, we are going to say that this decision problem belongs to the complexity class CoNP. Okay? So since such a certificate, notice that this can be checked easily. You can easily check. I'm not going to go into technicalities of easily. The right way to talk about it is polynomial time on a deterministic Turing machine. But if you're not familiar with those things, don't worry about it. It is intuitively clear that if the graph has a certain size, you can check quickly that the cost of m is strictly less than the cost of n. It doesn't require you to check exponentially many possibilities. Okay, and this will become clearer when we come to yes instances in a moment. Since such a certificate exists and can be verified easily, I'll just put this in double quotes because we are not going to go into those technicalities. The decision problem DP, min cost perfect matching, belongs to CoNP because this is for no instances. Okay? For NP, we want the same thing to happen for yes instances. Okay? So if you are a bit confused right now, don't worry about it. Just stay with me and it will become clearer once we discuss the yes instances. Okay? So now I want to ask the other question. How would you convince someone that M, the green one, is a minimum cost perfect matching? So let's write this down. How would you convince someone Okay, so we want to now convince the person that the green colored one is indeed a minimum cost perfect matching. Yeah, someone was about to say something. Go ahead.
Sir, can we try something like proof by contradiction, assume something lesser than this and arrive at a
Yes,
contradiction?
right. So how will we get a contradiction?
No idea.
No idea. Good. That
So I
is
think we need
yeah.
to
Go ahead.
run through all possible perfect matchings and then check it. That's the only
Right.
way, I guess.
That's okay. So that is one way. Luckily, that is not the only way. Okay. So this is exactly the answer I'm looking for. Intuitively, the obvious way to do it would be to go through all the perfect matchings in this particular graph and compute the costs of each of them, which is easy, and check that they are all greater than equal to 6 in this case. And therefore, M is indeed a minimum cost perfect matching. Okay? So, but that is a problematic thing because the number of perfect matchings in a graph can actually be exponential in the size of the graph. That is actually true for particular classes of graphs called cubic two connected graphs, but let's not go into graph theory. We can talk about that towards the end. The main point I want to make is that we can check all perfect matchings, but the number of perfect matchings can be exponential in size of the graph. So this is not an efficient way. This is not a certificate. Supposing I were just to list down all the perfect matchings in the graph and give it to my friend. Now my friend will compute the costs, but the problem is this is not a small certificate. This is all the perfect matchings of the graph, right? And that could be a very large number compared to the size of the graph. So that cannot be verified easily, unlike the previous case, right? So this is not uh, this is not an easily verifiable certificate. Okay, checking all the perfect matchings is not an easily verifiable certificate. Okay, so that is not a good way to certify yes instances. It does not work efficiently. So at this point in our discussion, we cannot conclude that this problem belongs to NP. So I'm just going to say, does it belong to NP?
It seems like it might belong to NP.
It might. It actually does, but it's not. I'm just going to say that not immediately clear unless we develop more theory.
Okay.
Unless we have more theory. Well, what I really mean is some mathematical theorem that helps us. Okay? So, in other words, we don't yet know how to get a certificate or whether always a certificate, I mean, it's not about finding it, sorry. We don't know whether a certificate always exists, whether there is any certificate that always exists for the yes instances, and we want the certificate to be easily verifiable, right? In other words, to put it more intuitively, we don't know how to convince someone that a given perfect matching is indeed a minimum cost perfect matching. The only way we know how to do it is by running through all the perfect matchings of the graph, and that is clearly inefficient. Okay? So are there any questions at this point?
So, like for the no instance, like how are you able to tell it's easily verifiable?
Right, right. So what is the certificate? Can you tell me what the certificate is for a no instance?
I mean, we need to find a matching which has a lower cost, but then,
Right.
but then how do you find a?
That's the misconception you're having, which is a very common misconception. We don't need to find the certificate. That is an algorithmic problem. Here we are talking about whether a certificate exists or not.
Right.
Okay. So we are not talking about the algorithmic problem of finding a minimum cost perfect matching or finding a certificate that shows that a perfect matching is not of minimum cost. Right? We are just talking about whether certificates exist or not. Right? We will talk about algorithms later in this course. But NP and co-NP are not about algorithms. They are about existence of certificates. And that is actually a very common misconception. Very common. Yeah, go ahead. Yeah, go ahead.
So, but just to add on to that, to say that it exists or doesn't exist is in turn finding it. I don't exactly understand how we would say that a certificate, for example, the certificate M exists without knowing that particular matching is there.
Right.
How would you say it exists?
Right. So let's try to abstractify it, right? So if a perfect matching is not of minimum cost, right, it is precisely because there is another perfect matching of lesser cost than this one. That's by definition, right? I'm not saying anything deep here. That's one of the things I want you to understand. That the way we said that this belongs to co-NP is not by some deep theorem. It is by the definition of the problem itself. Right?
Right. Okay.
So the problem of finding this perfect matching, whose cost is lesser, that is an algorithmic problem. But the existence of the certificate does not depend on whether we have an algorithm to find the smaller perfect matching or not, or the one of lesser cost.
Right. Okay.
Do you see the difference?
Yes.
Right. The existence is there.
Right. Right. Yes.
Yeah. So it is a slightly more abstract thing, but yeah, so it's good to clarify these doubts right now, right?
Yes.
Like one more doubt. In the other case, like where we say where we want to show is the perfect matching with the least cost. I mean, the certificate is we can show all other matchings are
Right,
higher, right?
right. The problem is it's not an efficient certificate because you will have to check for all the perfect matchings, and that could be exponential in the size of the graph. So that is why I wrote in double quotes here. It is not an easily verifiable certificate. If you want to make this precise, which you would do in a complexity theory course, you would say that it is not polynomial time doable on a deterministic Turing machine. But some of you may not have taken courses on complexity theory. That is why I don't want to go into these details. I just want to keep it at an intuitive level. Do you see at an intuitive level that this is harder to check than for our previous certificate, where we just need one perfect matching whose cost is lesser? Whereas here we need to look at all the perfect matchings of the graph and check that their cost is not less than the given one. Do you
I
see the
mean, like,
difference? Yeah, good.
I mean, like checking like here, we are sure we need an exponential thing, like, but
Right.
for the other certificate, like, we need to find a smaller one.
We
That
don't need
could
to
take.
find it. We don't need to find it. That is the key thing. We just need to know that it exists.
I mean, showing that it exists also
Right. So that is
could
the
be
algorithmic question.
right. Okay.
Right. So I can understand why this is a bit jarring, because we just know that the certificate exists because of the definition of the problem. There is no deep theorem that we used it, right? But finding it is an algorithmic problem. So how about this? Let's continue talking about how to convince someone that given perfect matching is of minimum cost. Let's continue talking about this, and then I'll come back to this discussion to make it clearer, right? Okay, so
Okay.
we are not done with this discussion yet. I still want to continue with this example that we have here. I want to convince you that the green colored one is indeed a minimum cost perfect matching. And the way I will convince you will seem a little bit ad hoc, but it will not require us to go through all the perfect matchings of this graph. Okay? Are you with me?
Yeah.
Okay, so once we go through that discussion, we will come back to NP and co-NP, and we will address this whole question about existence versus finding the certificate. And I think then it will become a bit clearer what I'm trying to say, in case it's not clear at this point. Yeah? Okay. Okay, any other questions or concerns? So we are going to continue with this example, and we are going to come back to NP and co-NP discussion once I have convinced you that this green colored one, M, is indeed a minimum cost perfect matching. Okay, good. All right, so let me see if I can copy paste to make life a bit easier. I think I should be able to do that. Okay. Copy and okay, great. All right. So here is our graph. Let me erase the red colored perfect matching to avoid confusion. Okay. I want to convince you without looking at all the perfect matchings of this graph. This graph, of course, has, I think, only 5 perfect matchings, so we could very well check it, but I don't want to do that. I want to convince you in a different way that this is indeed a minimum cost perfect matching. Okay? And that will take us back to the discussion on certificates. Okay? Good. So let's write it down. M is our green colored perfect matching. It has the edges UV, RT, and SW. Okay. And my goal is to convince you that M is indeed a minimum cost perfect matching in this example. Okay. To make it clear, without going through all perfect matchings. Okay. All right. So here is an idea. Whether this idea works or not is something we are going to explore in this course. But let's just start with what the idea is. Let me ask you the following question. Supposing I consider a particular vertex, let's say T, for the sake of example. Supposing I consider a particular vertex T and I change the costs of all the edges incident at this vertex by a constant number. Okay. Consider a particular vertex T and increment or decrement all the cost of all edges, the cost of each edge which is incident at the vertex T. Okay, by a fixed constant. Okay, so I'm going to construct a new cost function by taking the original cost function and making some small changes to it. Okay, what will happen in this case? Can someone tell me what will happen to the cost of each perfect matching? Supposing my constant is K, why not? Supposing I decrease everything by K, right? So let's say I put K equal to, let me see the example I have. Let's say I put K equal to 1 and my new costs are going to be, I'm going to take the original cost and decrease all of them by K. Okay, so I'm going to put the new costs in circles. Minus 2, 2 minus 1, 1, and 3 minus 1, 2. Okay, so for all the other edges, my costs are the same as before, but for these three edges, I have perturbed their costs by a constant. So my question to you is, what happens to the cost of each perfect matching?
So that decreases by 1 as well.
Right. Why?
And that's because in every perfect matching, there's exactly one edge incident at a vertex. So
exactly.
For this vertex in particular, you have each edge having the value decreased by 1. So
exactly.
That should
Right.
be it.
Right. So notice that for each perfect matching, by the definition of perfect matching, we are going to use exactly one of these three edges, right? And so the total cost of the perfect matching is going to go down by 1 as well, right? So notice that in this case, the perfect matching M now has cost 3 plus 1 plus 1 equal to 5. Okay, so the old cost of the perfect matching M was 6 and the new cost of the perfect matching M is now equal to 5. Okay, So which means that I can make a change at any vertex, and that will basically just change the cost of each perfect matching by that value. Okay, and so in particular, the minimum cost perfect matchings will remain the same. Do you all agree? If all of them go
Yeah.
down by one, the minimum ones remain the same, right? Okay, so in particular, note that cost of each perfect matching goes, okay, so in this case, goes down by k equal to 1, because that is what we chose k to be. Okay, and thus the set of minimum perfect matchings, set of minimum cost perfect matchings remains the same with respect to the new costs. Okay, are there any questions or concerns at this point? All right, so it's already 10:48. I don't know if I want to complete this example today, or should I just give it to you as a try it yourself and we discuss further tomorrow? All right, let me not go beyond 10:50. Let me just give you a try it yourself exercise here. So what I want you all to try is I want you all to come up. So notice that if you can make a change at one vertex, well, then you can make a change at every vertex, right? You just repeatedly apply the same argument. Okay, so what I want you to try is the following. Can you find or find labels for each vertex? So this k, think of it as a label for the vertex t. Okay, so label of t is equal to 1. And what we did is we decremented it from the cost of our perfect matching. Okay, so find labels for each vertex v. So let's call it L of v, such that as per the new cost. So how are we going to compute the new costs? For each edge, we are going to decrease the label for both the ends, right? Notice what we are doing here is for the edge RT, we are reducing its cost by 1, which is the label of the vertex T. So now we are going to reduce it by the label of T, and we are also going to reduce it by the label of R, because we are doing the same argument for each vertex. Okay, so such that as per the new costs C prime, so C prime is going to be defined as, for the edge UV, we are going to take the original cost of UV minus the label of U minus the label of V. And what I want is all of these new costs should be non-negative numbers, and the cost of the perfect matching M should become 0. Okay, such that C prime UV is at least 0 for all UV, and C prime of M is exactly equal to 0, where M is our green perfect matching. Okay, is the idea clear? So we want to find labels for each vertex, right, which is basically going to be a real number. So the labels, just to make it clear, L is going to be a function from the vertices of the graph to the real numbers. Okay, so in this example, we chose the label of t to be equal to 1, and we chose the label for all other vertices to be equal to 0, because we just made a change at t. Okay, and the new costs are going to be defined in this way. And we want to make sure that all the new costs are non-negative numbers, and in particular the cost of the perfect matching M magically becomes 0. I am not telling you how to find them. But I know that in this example, you can do that. Okay? Supposing you are able to do that, then what does it mean? Can anyone tell me? Supposing you are able to find such labels, what does it mean?
I mean, M will have the smallest cost.
Exactly. Then
Every
n will be a minimum cost perfect matching in this new in the new costs. But then it will also be a minimum cost perfect matching as per the original costs, right? Do you agree?
yeah.
Because of the observation we made here. The set of minimum cost perfect matchings is not going to change by doing this operation. Okay? So this is what I want you to try. This is the, but if such labels exist, then we actually know that M is a minimum cost perfect matching. And that is going to be our certificate. If you didn't follow all the discussion, don't worry. We will go through this formally again tomorrow. And we will see that for this example, you can actually find a certificate. Can you find it for all graphs? That is something we are going to explore in this course. And you might think that this is a bit of an arbitrary idea. It will become clear when we study linear programming theory. And one of my motivations is to give you a flavor of the expectation of graph theory in this course so that you are able to assess whether you are prepared for that or if you need additional preparation. And I also want to sort of intrigue you to get you interested in the theory of linear programming that we are going to explore using this example. Okay? So this might seem like an arbitrary ad hoc idea. It is not ad hoc, as will become clear by module 4 for sure, but maybe even earlier. Okay, so the lecture is officially over. If you have any questions or concerns, please stay back. I'm here for another 10 minutes. Is the question clear what you are supposed to try? When I say try it yourself, I generally mean that we are going to do it in the next lecture. Or the problem is difficult, it might even appear on assignments, but that is not the case here. We are going to continue this example tomorrow, and we are going to see that such labels do exist for this graph.
So, like, is this linked to like solving linear equations, like the Gaussian elimination? Like, it seems somewhat linked to that.
Right. So it's actually linked to solving linear programs. It's related to the simplex method that we'll be studying. So Gaussian elimination is good for solving linear equations, but in general, we want to solve linear programs, and we are interested in optimizing the objective function. So we need something more sophisticated than that.
Yeah, right. I mean, we are choosing k such that, I mean, so all the equations are the same, but we're trying to manipulate the equations, something like that.
Right. Exactly. Yeah. Are there any other questions or concerns? Krishnan, Madhav?
I don't have anything in particular.
Okay. Okay. Is everything followable so far?
Yeah, it's fine.
Okay. Cool. Thanks.
Yeah.
Madhav, are you there? Okay. I guess you're not there. I'm going to stop recording now.